Tectonic plates. You've probably heard of them. You might have a rough idea of what they are. So let's talk about plate tectonics in a bit more detail. Then we're going to apply that theory to see what exactly was going down when a specific earthquake happened. Let's get started. You've most likely heard that the Earth is split up into separate layers: the crust, the mantle, and the core. The crust and the mantle are what we're concerned about here, so ignore the core. The crust and the very top parts of the mantle make up the lithosphere. Now, the lithosphere isn't constantly laid out over the surface of the Earth. The lithosphere is split up into many different pieces, called, wait for it, tectonic plates. There are 8 major tectonic plates, plus a lot of minor plates, which in decreasing order of size are the Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Australian Plate, and the South American Plate. You may be asking, how exactly do we know the Earth is split up into all these plates? Well, Mr. Imaginary Voice, though obviously we can't observe the tectonic plates directly, we have a bunch of different pieces of evidence that point us towards the existence of tectonic plates. One major thing that tectonic plates do is move over time towards and away from each other. We'll go deeper into this in a minute. The first evidence that we had of plate tectonics was that a bunch of map makers noticed that South America and Africa looked like they could be joined together neatly, as if they were once joined and moved away from each other over time. Later on, we got evidence that was a lot better than the continents look like a jigsaw puzzle. There are two other main pieces of evidence for tectonic plates that I want to show you. The first being that the fossil record shows plants and animals that appear to have a common ancestor often live on parts of continents that would have been joined by Pangea. The second piece of empirical evidence that we have is that once we started monitoring earthquakes, the places where earthquakes happened seemed to form lines outlining where the tectonic plates were. Why would earthquakes have anything to do with tectonic plates? Well, I'm going to talk about how earthquakes are formed right about now. In the simplest terms, an earthquake is caused when 2 of the tectonic plates really suddenly and quickly slip past each other. The slip causes a bunch of rocks in the area to break up and slip past each other more. This creates pressure, which is released by having the ground shake. The first round of shaking is called the foreshock, and it can trigger different smaller quakes called aftershocks, and so we have an earthquake. The visible crack in the earth that is caused by the tectonic plate slip is called a fault. There are 3 main types of earthquake-causing faults. Strike-slip faults are where the line of the fault, or fault lines, are more or less straight up and the slipping is directly side to side. Normal faults, where the fault line is diagonal and the plate facing the slope as it were slips down said slope. And reverse faults, where the fault line is diagonal and the plate facing the slope slips up. Let's go a bit more into detail of the parts of a quake when the slipping happens. The spot underground where the rocks broke is called the focus and is the center of all energy that makes the earthquake happen. The spot on the surface of the earth directly above the focus is called the epicenter, which literally translates to above the center. This makes stuff like when Apple calls their WWDC the epicenter of change a bit weird, because that means it's above the center of said change. Anyway, moving on. The energy waves that are released making the shaking of the ground that we associate with earthquakes are called seismic waves, which is why we measure earthquakes with a seismometer. On the topic of measuring earthquakes, on what scale do we do that? You've probably heard of the magnitude scale before, so I won't go that much into the basics of what it is. Essentially, any earthquake above a 6 on the scale is when we should start seriously worrying. But how does the scale work? Is it arbitrary, or is it based on some external standard? Yes and no. The moment magnitude scale, which will now be referred to as the MMS in this video, is sort of arbitrary in terms of where to place the numbers, but it is based off of measurable energy scales using insanely complex formulas. Another thing to note about the MMS is that instead of it scaling linearly, i.e. the difference in energy between 1 and 2 being the same as the difference between 2 and 3, the MMS scales exponentially by powers of 10. So 2 is 10 times more than 1 and 3 is 10 times more than 2. Before I move on, I would like to note that there is another scale on which earthquakes are measured, the Mercalli scale, which has more to do with damage done by the earthquake instead of its energy. But for the sake of keeping this video a reasonable length, I won't go too in-depth. That's everything I have to say about plate tectonics theory and its relation to earthquakes. Now let's apply the theory to an actual earthquake. At either 5:12 or 5:13 a.m. Pacific time on April 18, 1906, a strike-slip foreshock occurred in Northern California on the San Andreas Fault, causing noticeable tremors. The full force of the seismic waves came up about 30 seconds later with an epicenter almost directly on San Francisco. Silicon Valley wasn't really a thing at this point, so no, people didn't have to worry about Google servers failing. At least 1,000 people died, and the quake and the resulting fires destroyed a majority of the city's buildings. Adjusted for inflation, the total damages cost over $6 billion US. Along with Hurricane Katrina in 2005, the quake is considered one of the worst natural disasters in US history. But let's detach from the tragedy and look at the science of the situation. I already explained that the quake was strike-slip, so I don't need to go over that. But there are still quite a few scientific facts to go over. The focus of the earthquake was right next to what is now Daly City, California, which is just south of San Francisco. The rupture in the ground created by the tectonic plates moving was almost 500 kilometers long. Because the earthquake is over 100 years old, we don't know exactly what the magnitude of it was, but the estimates put the magnitude around 8, and around an 8 or 9 on the Mercalli scale. The fault line that this quake occurred on, the San Andreas Fault, is arguably one of the most famous in the world. Every year, countless quakes occur on this border between the North American Plate and the Pacific Plate. Actually, everything bordering the Pacific Plate has a higher natural disaster output, be it earthquakes or tsunamis or volcanoes. This area around the Pacific Plate is called, fittingly, the Ring of Fire. I could go on and on about more things with this earthquake, like how the aftershocks played out or what aid was sent, but this video must end. Welcome to the outro screen. This video was pretty fun to make, and I learned quite a bit about tectonic plates, earthquakes, and the San Francisco quake, and I hope you did too. The script for this video turned out to be quite a bit longer than I imagined, but it turned out pretty well. You can find a link to the script, the image credits, and citations for the video in the description. Special thanks to 2 different U.S. federal government departments, the U.S. Geological Survey for having a bunch of info about tectonic plates and the San Francisco earthquake, and the U.S. Library of Congress for having a bunch of images of the San Francisco earthquake that are in the public domain. I hope you enjoyed this video, and now I shall bid you farewell.